This is a phone, using an internal gyroscope to simulate a virtual gyroscope that maintains its orientation relative to the outside world, independent of the orientation of the phone. The iPhone has a local coordinate system with 3 axes, x, y, and z. We can also define 3 Euler angles, pitch, yaw, and roll, to represent rotations about each axis. Here we can see that the gyroscope counter-rotates to account for rotations about the x, y, and z axes. This is possible because for every frame of animation, the internal gyroscope gives us 3 numbers, the angular velocities about the x, y, and z axes. But these aren't that useful in their current form. What we really need for the animation are the angular velocities of the middle ring, the inner ring, and the cube. Notice that the outer ring is static. We can solve for these velocities with the following 3 equations which I made up. The first one is pretty obvious. If the phone is rotating about the x-axis, the middle ring needs to rotate by the same amount but in the opposite direction, hence the negative sign. For the inner ring, let's look at 2 cases. If theta x equals 0, then the axis of the inner ring is aligned with the z-axis. Therefore, its rotation rate should be equal to the z rotation rate. If theta x equals pi over 2, the inner ring is aligned with the y-axis, and therefore its rotation rate should be equal to the y rotation rate. And for all other cases, its rotation rate will be some combination of the 2. The second equation is one such combination, which seems to work. The third equation can be derived by similar means, but I'll leave that as an exercise for the viewer. Notice that these equations make use of the angle about the x-axis, but the gyroscope only gives us the rate of change of that angle. So to get that angle, we just need to integrate its rate of change. I go into more detail about this in my black hole video, so check that out if you care. It's entirely possible these equations are totally wrong, but they look right to me. This method of maintaining orientation has a big problem that has plagued many mathematicians: gimbal lock. This occurs when all 3 rings are aligned, like this. In this situation, we lose the degree of freedom because there is no way to rotate the cube about the z-axis. If we try to rotate the locked gimbal about the z-axis, it totally fails to maintain orientation. The whole point of this project was to stabilize a world in virtual reality. To do that, we just have to fix the virtual world to the cube and then render it twice from 2 cameras, one for each eye. Then display the 2 images side by side on the screen, and the lenses in the headset will do the rest. I tried it and was pleasantly surprised at how well it actually worked. It's basically just a buggier version of Google Cardboard. The gimbal lock is pretty nauseating when it happens, and it's a big enough problem to warrant designing a new stabilizer that doesn't rely on gimbals. This isn't on the App Store, but you can get the code from my GitHub, link in the description. It's an Xcode project, so MacBook Pros only. If you like this, check out the black hole video and subscribe, because I'll probably make another video sometime in the next decade.